Now we discuss about the classification of periodic table into S, P, D and F blocks, which is based on electronic configuration. Now you take any period, just we observe what is the electronic configuration for this. The first period is very short period. It has hydrogen and helium. The electronic configuration for hydrogen is 1s1. The electronic configuration for helium is 1s2. Similarly, you take second. The first one is the lithium. The last one is neon. This period has 8 elements. The electronic configuration for lithium is 1s2, 2s1. Similarly, for neon it is 1s2, 2s2, 2p6. Now what you are observing here? Yes, in this period, the electrons are filled in two shells. In first period, the electrons are filled in one shell only. Similarly, we take third period. The first one element is sodium. The last one is argon. The electronic configuration for sodium is 1s2, 2s2, 2p6, 3s1. For argon is 1s2, 2s2, 2p6, 3s2, 3p6. Here we find three shells are filled. The electrons exist in three shells. From this what we can conclude? Yes, the number of period indicates the value of principal quantum number for the valence shell. Already you know what is valence shell, outermost shell. Here the outermost is first 1. In this case it is 2, second period. 3, third period. That means the principal quantum number for the valence shell and the total number of shells present in atom is constant across a period. Similarly, if we consider the electronic configuration for a group, then what we can observe? I am taking first group, hydrogen and alkali metals. The electronic configuration for hydrogen is 1s1. For lithium, what is atomic number of lithium? Yes, it is 3. The electronic configuration for lithium is 1s2, 2s1. It can be written as helium 2s1. Similarly for sodium, 1s2, 2s2, 2p6, 3s1. Simply it can be written as neon 3s1. Similarly for potassium, the atomic number is 19. The electronic configuration you can write argon 4s1. The number of electrons in different shells 2881 in the case of potassium. Similarly, we take rubidium. The atomic number is 37. The number of electrons in different shells are 281881. This can be written as krypton 5s1. Similarly, we take cesium. The atomic number is 55. The arrangement of electrons in different shells are 2, 8, 18, 18, 8, 1. The electronic configuration simply we can write xenon 6s1. For francium, the atomic number 87. The arrangement of electrons in different shells are 2, 8, 18, 32, 18, 8, 1. The electronic configuration can be written as radon 7s1. Now what you are observing here? In this group, for every element, the outermost orbital is same. That is, the azimuthal quantum number related to valence electron is same. Or we can say the last electron, the differentiating electron, entering into the same orbitals in this group for every element. Similarly, we take group 2. What are group 2 elements? Beryllium, magnesium, calcium, strontium, barium, radium. If we observe the electronic configurations of these elements, for barium it is helium 2s2, for magnesium it is neon 3s2, for calcium it is argon 4s2, for strontium krypton 5s2, for barium xenon 6s2, for radium radon 7s2. Here also we observe the azimuthal quantum number, that is valence electron orbital, is same. Similarly, we take boron family. For boron family, the electronic configuration for all these elements can be written in form of Ns2Np1. For carbon family, it can be written as Ns2Np2. For alkali metals, it is Ns1. For alkaline earth metals, it is Ns2. Therefore, we can conclude we use this similarity, that is a similarity in electronic configuration, to understand many of the chemical and physical properties of the elements. And based on this, we can divide the long form of periodic table into four divisions. They are S, P, D, and F block elements. And this classification is based on the type of atomic orbitals to which the last electron, that is differentiating electron, enters. On the basis of electronic configuration, the elements are grouped into four blocks. They are S block elements, P block elements, D block elements, and F block elements. S block elements. These first two groups are called S block elements. In this, the differentiating electron enters into outermost S shell, that is NS1 or NS2. And these have NS1 NS2 configuration that followed with N-1 S2 P6 or N-1 S2. This is in case of lithium and beryllium. NS1 for alkali metals and NS2 is alkaline earth metals. This is group 1 and this is group 2. Already we discussed about the electronic configurations of these two groups. And next one is P block elements. If you observe the groups from 13th to 18th, in 13th group, the elements are boron, aluminium, gallium, indium, and thallium. And the electronic configuration for this 13th group, that is the electronic configuration of outermost shell, is for boron it is 2s2 2p1, for aluminium it is 3s2 3p1, for gallium it is 4s2 4p1, for indium it is 5s2 5p1, for thallium it is 6s2 6p1. That is here 2 electrons of S and 1 electron of P. In general, we can write it as NS2 and P1. Similarly, in carbon family, the electronic configuration for outermost shell of carbon is 2s2 2p2. For silicon, it is 3s2 3p2. For germanium, it is 4s2 4p2. For tin, it is 5s2 5p2. For lead, it is 6s2 6p2. Here also we can observe 14th group contains 2 electrons of S and 2 electrons of P. In general, the outermost electronic configuration is in form of NS2 and P2. Similarly, for 15th group, the outermost electronic configuration, just you see this table, yes, it is in form of NS2 and P3. For 16th group, yes, it is in form of NS2 and P4. For 17th, it is in form of NS2 and P5. For 18th, it is in form of NS2 and P6. Now what we are observing here, the differentiating electron enters into p orbital of the outermost shell. The last electron is in the p orbital of outermost shell. Hence, these groups are named as p block elements. And next one is d block elements. Now between S and p blocks we are having d block. And in these elements, the differentiating electron enters into N-1 d orbital. And these groups 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. That is total 10 groups. This is called d block. Suppose we take the electronic configuration of scandium. The atomic number is 21. The electronic configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1 and 4s2. Similarly, for zinc, the atomic number is 30. The electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Here what we can observe? Yes, scandium to zinc, this is related to 4th period. Here the differentiating electron entering into 3d, and also we can find that here the two shells, they are having incomplete electronic configuration. For this, third one as well fourth one, both are incomplete. And here we can find the electronic configuration for last shell says N-1 S2 P6 D1 to 10 and NS 1 to 2. Similarly, we consider yttrium to cadmium. The electronic configuration for yttrium to cadmium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d, 1 to 10, 5s2. This is fifth period. The differentiating electron enters into 4d, that is n minus 1 into d orbital. Similarly, for this period, for sixth one, the electronic configuration for the outermost shell is in form of 5s2, 5p6, 5d, 1 to 10, 6s2. The elements are Aphenium to mercury, and their electron enters into 5d n minus 1 into d. And in complete series, that is seventh period, it is an incomplete. Here we have actinium, rutherfordium and dubinium. Here the outermost electron enters into 6d subshell. And this is called d black elements. Where electron enters into 3d shell, it is called 3d series, that is scandium to zinc. Where differentiating electron enters into 4d, it is called 4d series, it is yttrium to cadmium. When differentiating electron enters into 5d, it is called 5d series. This is Aphenium to mercury, and the last one is actinium, rutherfordium, dubinium. This is an incomplete series. The differentiating electron enters into 6d subshell. It is 6d series. And this is d black elements in the periodic table. And f black elements. In these elements, the differentiating electron enters into n minus 2 into f orbital. And elements having 3 incomplete outer shells, they are known as inner transition elements, or f black elements. And they have the configuration n minus 2 into s2, p6, d10, f1 to 14, n minus 1 into s2, p6, d0 to 1, and s2. There are two series of f black elements corresponding to the filling of 4f and 5f orbitals. One is the lanthanoid series. Here the differentiating electron occupies 4f subshell. Suppose we take the electronic configuration of lanthanium. The atomic number is 57. It is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f0, 5s2, 5p6, 5d1, 6s2. Similarly for cerium, the outermost electronic configuration is 4f1, 5s2, 5p6, 5d1, 6s2. And the last element in this series is lutetium. The outermost electronic configuration for this is 4f14, 5s2, 5p6, 5d1, 6s2. The differentiating electron occupies 4f subshell. And another series is there in F block, it is actinoid series. And the differentiating electron occupies 5f subshell here. If I take the electronic configuration of actinium, the atomic number is 89. Say this outermost configuration. The configuration of outermost shells, 5f0, 6s2, 6p6, 6d1, 7s2. Similarly, for thorium, with atomic number 90, the configuration of outermost shells, 5f1, 6s2, 6p6, 6d1, 7s2. What you are observing here? Yes, the differentiating electron enters into 5f subshell. And these octanides are radioactive elements. And the elements from atomic number 93 onwards are called transuranic elements, and they have been made artificially. G.T. Seeberg has significantly contributed in the discovery of these elements. Differentiating electron. This is the electron that enters in the last valence subshell, that is ns, np, or n-1 into d, or n-2 into f. This decides the properties of the atoms. At a nutshell, the important characteristics of S, P, D, F black elements are: first, S black elements. The electronic configuration of outermost shell of S black element is Ns1 for alkali metals, Ns2 for alkaline earth metals. There is group 1 and group 2. These two are called S black elements. The valency of group 1 element is +1, and for group 2 it is +2. These are soft metals having low melting points and boiling points, and most of these form ionic compounds on account of their low ionization energies. Since their ionization energy is low, most of them form ionic compounds. And most of these metals and their salts impart characteristic color to the flame. For example, if sodium is taken, it imparts a golden yellow color. Potassium imparts violet to the flame. When it is exposed to the flame, it gives golden yellow color, it gives violet color. They are highly reactive elements and strong reducing agents. And these are all good conductors for heat and electricity. Next, P black elements. Group 13 to 18, this is called P black. And the electronic configuration of outermost shell is Ns2 Np126. These elements includes metals, non-metals and few metalloids. These are metals and these are non-metals and these are metalloids. And these possesses a relatively higher ionization energy, which tends to increase along the period, but it decreases down the group. And most of them form covalent compounds. And most of these elements show negative as well as positive oxidation states. The oxidizing power of these elements increases along the period but decreases down the group. The next one is D black elements. In between S and P black we are having D black elements. The electronic configuration is in form of N-1 into D1 to 10 NS0 to 2. Except mercury, all are hard and ductile and they have high melting and boiling points. All of these are good conductors for heat and electricity. The ionization energies of these elements are more than S black, less than P black elements, and most of the transition elements form colored ions. These elements show variable oxidation states. These elements possess catalytic activity, and metals and ions are generally paramagnetic due to presence of unpaired electrons. Most of the transition metal ions possesses the tendency to form complex ions by coordinate bonds, and most of these metals form alloys. And next one is F black elements. The electronic configuration of outermost shell for these F black elements is N-2 into S2 P6 D10 F1 to 14, N-1 into S2 P6 D0 to 1 NS2. All these are metals. These lanthanides are also known as rare earth elements, whereas most of the members of actinoids are known as transuranic elements. These are made artificially. They show variable valency, they form colored ions, and these actinoids are radioactive. They also form the complexes. And these are the properties of S, P, D, F black elements.